Jay. All right, Jay's a fourth-year medical PhD student at Arizona State University and a research focus on using machine learning to identify clinical biomarkers for early detection of Alzheimer's disease and headache phenotypes. His primary research interest lies in deep learning, computer vision, and medical imaging.
All right. Good afternoon, everyone. My name is Jay Shah from Arizona State University, and today I'll be presenting my research on detecting brain age signatures in persistent post-traumatic headache. These are my disclosures. To give a bit of background, migraine and post-traumatic headache are common primary and secondary headache disorders. Post-traumatic headache, or PTH, is a symptom that follows mild traumatic brain injury, and if headache lasts less than 3 months, we consider them to be acute PTH patients, and if it is more than that, we consider them persistent PTH patients. Migraine-like phenotype is commonly observed in PTH. However, the underlying pathophysiology of persistence in PTH is very poorly understood, mainly because it is multifactorial, and it is an active area of interest among researchers to understand the similarities and differences between migraine and aPTH phenotypes. So the question is, can we differentiate between migraine and PTH phenotypes? T1-weighted MRI scans can tell us more about the brain atrophy and volumes, which can lead us to quantify brain shrinkage, which is typically known to be associated with aging. And back in 2016, some researchers showed that using AI, we can indeed predict the biological age using MRI scans. And since after that, people have used multiple types of datasets, multiple types of methods to understand something called aging clocks. And the goal is to understand this aging clocks to explain different biological process in the whole body, not just brain. And so broadly, we want an AI model that can capture the whole natural aging process, primarily in this case using brain MRI scans, and use that model to understand how the accelerated aging effects look like. And so primarily, we are interested in learning about a measure called brain age gap, which is the difference between the model's predicted age minus the actual age. In a separate research, we showed that when we collect 5 different clinical groups among the Alzheimer's disease spectrum in an increasing order of severity, the model's predicted delta age was actually positively correlated with disease severity. What it means is that this particular measure, delta age, can quantify the accelerated aging effects in a very similar fashion as the disease gets more and more severe. So the question in this research I'm trying to understand is, are there any brain aging signatures indeed in persistent PTH that we can detect using AI models? And can we use those analyses to understand better how the similarities and differences between all of these headache phenotypes can look like? So to train the model, I collected more than 7,000 scans from 5 different public cohorts, and all of these are healthy scans. And for the headache phenotypes, we collected more than 300 scans from Mayo Clinic in Arizona. And typically in literature, people have trained the models by regressing the age values on top of healthy subjects using a deep neural network. And then once the model is trained, you give it a diseased subject to predict the delta age values, which is the predicted age minus actual age. But a classic problem that normally happens is when you frame this problem as a regression, there is a systematic bias inducted into the model, because when you train it using mean square error, you will see that younger subjects will constantly be over-predicted by the model, and older subjects will be constantly under-predicted by the model. And this particular problem has been drafted in literature for a very long time, but the solution is not out there yet. And why this particular bias matters in this case in neurological disease detection is typically for Alzheimer's and Parkinson's diseases, most of the patients happen to be old subjects, so we need to correct this bias. So in order to tackle this particular problem and remove this bias and improve the brain age prediction, what we propose in this model is, first of all, we remove the regression part. We frame this problem as a classification. So instead of model predicting an age value, the model is predicting an age label. And on top of this, we introduce a new loss function to train the model called order loss. And the goal is very simple. I want to force the model to actually understand how the age values of all of these patients are in relation to each other. So from this particular illustration that I'm showing over here, a normally classification model treats all of these patients as different, but it doesn't understand what an age sample of age 20 looks like, what a sample with age 40 looks like. So I want to force the model to understand that age 40 is much more closer to 20 and not to 80. And this is one of the illustrations. So this is how the deep learning model sees samples in its high dimensional embedding space. So on the left-hand side, when you see the sphere, that is from the classical classification model using cross-entropy loss. So you can see all of the samples are pretty much scattered. It doesn't have any understanding of what young patients are, what old patients are. But when we use our loss function to train the model is actually able to learn a smooth trajectory going from young patients to old patients. So it has some relative understanding of what all of these age values are. And once the model is trained, we test it out on an unseen test set from the healthy cohort, and we collect 4 different state-of-the-art methods that have been popular in brain age prediction, and we compare, and you can see using the mean absolute error, our model outperforms most of the methods by a 2.56 value. And on top of this, you can see that it also reduces the systematic bias on the younger cohort and older cohort respectively. And more interestingly, when we take this model and apply to headache phenotypes, this is where we have some interesting results. So from this particular plot, if you see the last 2 plots from the right-hand side, which correspond to migraine and persistent PTH, we indeed see that the model, these particular patients have some accelerated aging effects, because the delta H value, which is the y-axis, is higher for those 2 values. And we also see some cumulative effect of having headaches. So persistent PTH patients were the people who had headaches for more than 3 months, and you can see they have some accelerated aging effects. So there is a kind of effect that having more headaches can lead to more amount of aging effects. And on the other hand, acute PTH showed very subtle aging signatures, but I think it's very useful for early detection. And on top of this, I wanted to also understand how these groups vary using the delta, like the model's predicted delta H, because I want to understand how these different groups compare to each other. And we can see that migraine and persistent PTH, they both had very significant accelerated aging effects, much more similar to each other, because the p-values from all of these delta H across the different cohorts were much more less. And on the other hand, acute PTH was much, much more different than persistent PTH, which is an important biomarker, because I can now distinguish acute PTH patients versus persistent ones. So key takeaways from these particular results are that, yes, indeed, persistent PTH patients showed some effects of accelerated aging. So we have some kind of aging effects which has never been explored before. Headache frequency tends to have like a cumulative effect. Having more number of headaches can lead to aging effects, which is much more similar in neurological diseases. Migraine also had similar aging signatures. They were not as severe as persistent PTH patients, but definitely more than acute and healthy controls. And in terms of relevance for this particular research, I think delta H, which is commonly studied in Alzheimer's, I think it's also very useful as a potential biomarker for predicting persistence in PTH. Lastly, I'm very thankful to all the collaborators and advisors from Arizona State University and Mayo Clinic who have helped me shape this research. I'll take any questions if you guys have.